All right, this is chapter 6, starting with question 1. Question 1, it says, what is a fluid? A fluid is a liquid or a gas. It encompasses both liquids and gases, or gases. It's anything that flows. So fluid means to flow. Anything that flows, a liquid or a gas. Question 6. Name and state the principle upon which hydraulic systems are based. That's Pascal's principle. And Pascal's principle just says that if I have a container and I apply a certain pressure to it, if there is an incompressible liquid, the liquid inside of here has to be incompressible. That if I apply a force here over a certain area here, that applies a certain pressure to that incompressible fluid, and that same pressure is felt throughout the container. So if my pressure is force over the area, that same pressure is felt on all sides of the container and all throughout that liquid. How does a hydraulic system achieve an increase in force? All right, a hydraulic system works like this. We had this figure in class where my area over here is smaller than my area over here. So I put in a certain force. I'll call this force 1, and I'll call this A1. And since I can put a small force over a small area and then get a big force over a big area so that the pressures are constant. So Pascal's principle just says that the pressure over here, P1, is equal to the pressure everywhere else in the container, including right here. And so I can say then that F1 over A1 equals F2 over A2. So I can get a big force out by putting in a small force. Can one be used to decrease force? Sure, you could just reverse this. I can put in a big force here and then get out a small force here just by reversing that. I can't think of a good example where that occurs, but I'm sure that there are some scenarios where you need to put in a big force and then get out a very, very small force, just a very minute force. Maybe, possibly in some medical applications. I'm not really sure. All right, number 10. Explain in terms of equation 6.4 why I can notice a change in atmospheric pressure when you take an elevator in a tall building. Let's see, what was equation 6.4? Oh, it was P equals rho GH. So the pressure is equal to rho times G times H. Remember, if I had a container and I have a block in it, this pressure at this point is equal to the weight of the material that sits on top of this column above that object. And so it's a certain height h, and that pressure is equal to the weight of that column over the area. And we showed this in class, but it's equal to rho times G times H. So when you go deeper underwater, your pressure increases. And as you go up in the atmosphere, your pressure decreases. So let's see, the question was asking why you can notice a change in atmospheric pressure when taking an elevator in a tall building. So here's your tall building. As I go up in it, I'm decreasing that height of I'm right here. I have a column on top of me, H. It goes all the way up to space, and it's filled with air. All right, but as I go up in the building, I decrease the height of that column. I decrease it so that I only have this material that's sitting on top of my head. So that pressure has decreased. About how large is the total H creating atmospheric pressure at sea level? Well, let's see. The pressure at sea level is 1 atmosphere. and that's equal to 1 times 10 to the 5th newtons per square meter. I'm going to pull up our equation sheet. I want to look for the density of air. Notice that I adjusted your equation sheet, so there are some new things on here. The density of air is 1.29 times 10 to the minus 3. So the density of air is 1.29 times 10 to the minus 3. That was in kilograms per cubic meter, I believe. No, it's in grams per cubic centimeter. Let's look it up. 1.29 kilograms per cubic meter. Oh, you gotta love Google, right? 1.29 kilograms per cubic meter is the density. This is in grams per cubic centimeter. And it's 1.29 kilograms per cubic meter. That's the density of air. And so if I just want to do a rough calculation for H, what is the height of this column of air that sits on top of your head? It's going to be P over rho G. The pressure over rho times G. That pressure is 1 times 10 to the 5th newtons per square meter divided by 1.29 times 9.8. Or just times 10 meters per second squared. So that's 1 e to the 5. And I get 7,800 meters. So that's assuming that the atmosphere is about 7.8 kilometers above our head. That's actually a bit of an underestimate because the density of air will actually decrease as you go up. So you actually get a slightly higher level of, I have 7,800 meters of air that's sitting above my head that pushes down onto me that causes the pressure that I feel at sea level. All right, problem number 1. It's really kind of fascinating when you think about it, I think, that you have this huge column of air that sits on top of your head, and wherever you go, you always have this 7,500 kilometers of air, 7,500 meters of air sitting on top of your head. I think that's interesting. All right. As a woman walks, her entire weight is momentarily supported on the heel of one shoe. Calculate the pressure exerted by the floor on a high heel shoe worn by a 50-kilogram woman. So the mass of this woman is 50 kilograms. If the heel has an area of 2 centimeters squared, so the area is 2 centimeters squared, express the pressure in newtons per square meter and in atmospheres. We don't do powers. I'm not going to do it here. I'm just going to .0002. You will not have to convert between units with powers in that way. You might have to convert, say, from kilometers to meters or centimeters to meters, but not from centimeters squared to meters squared. All right. So I want to express the pressure. All right, remember, pressure is just force per unit area. So I have this lady, and she has this heel. She momentarily balances on this heel. So all of her weight is pressing down on that one heel. And so that's going to be the force weight over the area. That's M times G. That's 50 kilograms times 10 meters per second squared. That's her weight. She's 500 newtons. Divided by 0.0002 meters squared. That's the area of her shoe. so that's 500. And I get 2.5 million pascals. 2.5 times 10 to the 6 pascals are newtons per square meter. And it also asks to express this in atmospheres, so I can do a conversion here, and you will need to know how to do this. 2.5 times 10 to the 6 newtons per square meter. And then I multiply it by a conversion factor like we did back in chapter 1. In 1 atmosphere, there are 1 times 10 to the 5th pascals, or newtons per square meter. And so this is going to be 25 atmospheres. That's a whole lot of pressure, and we feel this at 25 atmospheres. So 25 times the pressure at sea level, 25 atmospheres. All right, let's see, what number was that? That was 1. Number 6. Calculate the force must be exerted on the master cylinder of a hydraulic system to lift a 10,000 kilogram truck with the slave cylinder. The master cylinder has a diameter of 1.5 centimeters, and the slave has a diameter of 30 centimeters. All right, so this is similar to what we did in class. It's using some slightly different language. If you've ever worked on your car, you know that your brake system has a master cylinder and a slave cylinder. The master cylinder is that small cylinder in this figure. So this is my master cylinder. It has a very small area, and that's where you put the input force. And then this is the slave cylinder. It's the one that actually does the work in picking up what it is that you want to pick up. So here I have a 10,000 kilogram truck. The mass of this is 10,000 kilograms. And my area here is 30 centimeters. I'm going to call this A2. Not the area, the diameter. I'll call it D2 is 30 centimeters. And over here, this diameter, I'll call it D1, was 1.5 centimeters. All right, now I want to know what is the force that has to be put in over here. I'll call this F1, and then this is going to be F2. Now F2 is equal to the weight of the truck. That's 10,000 kilograms times 10 meters per second squared. That's equal to 100,000 newtons. All right, so this truck has not 100,000, 10,000 newtons. No, that was right, 100,000. Sorry, 100,000 newtons. All right, now I can say that P1 is equal to P2. That is that F1 over A1 is equal to F2 over A2. I'm going to solve for F1. In order to do that, I multiply both sides by A1. And I get that F1 equals F2, which is 100,000, times A1 over A2. Now, A1 is the area of the circle. That's pi times the diameter over 2 squared. This is going to be D1 over pi times the diameter over 2 squared. The pi's cancel, the 2's cancel, so I'm left with D1 squared over D2 squared. That's 100,000 newtons. I can leave these in centimeters because the units cancel out. 1.5 squared over 30 squared. It should give me a much smaller force, and that'll be my answer. 100,000 times 1.5 squared divided by 30 squared. Oh gosh, really? That's not right. Let me try it again. Yeah, 250 newtons. So in order to lift this truck, I have to put in a force that's approximately equal, if we think back to the previous problem, about the half the weight of a small woman, about 250 newtons. A very small woman, actually. All right. Let's see, that was problem number 6. Number 19 is next. What is the density of a piece of wood that floats in water with 70% of its volume submerged? So I have this piece of wood and if 70% of its volume is submerged, 70% or 7/10, 0.7 times its total volume. So if the volume of the block is V, then 0.7 times V is submerged. All right. I know a couple of things. I know that the weight of the block is a certain amount. And I also know that because this is bobbing, it's not sinking, it's just sort of floating there, that I have a buoyant force. And that buoyant force is going to equal the weight of the block. I also know that the buoyant force is equal to the density of water times the volume of the block times G. This is Archimedes' principle. In this case, it's not the volume of the block, it's 0.7 times the volume of the block because that's the amount that is submerged. So I can set these two equal and say that the weight is equal to the buoyant force. So force weight is equal to the density of water times 0.7 times the volume, that's the submerged volume, times G, because 70% of the volume is submerged. Now, what am I looking for here? I want to know the density of the wood. All right, so over here, the weight is M times G, and that's equal to the density of water times 0.7 V times G. Notice that my G's cancel out. And now I want to know what is the density of wood. And the density of my wood is going to be the mass of the block over the volume of the wood. All right, so notice here that if I divide both sides by V, that this will be equal to the density of the wood. Be careful because here this is the density of the water, not of the wood. So my density of the wood is equal to the density of water times 0.7. Density of water is 1 gram per cubic centimeter times 0.7. So that's equal to 0.7 grams per cubic centimeter. It's a nice little feature, right, based on this density of water, that whatever fraction of the object that is floating above that is submerged, that is equal to the density of the object. All right, and also notice that the density of this wood is less than the density of water, and that's why it's floating. If the density of the wood was greater than the density of water, of course it would sink all the way to the bottom. All right, number 23. In a measurement of man's density, he is found to have a mass of 65 kilograms in air and an apparent mass of 1.5 kilograms when completely submerged in water with his lungs empty. What mass of water does he displace? All right, so I have this man. He has a mass equal to 65 kilograms. Then I put this man in a tank of water, completely submerged. He has no air in his lungs. And then the apparent mass is less than that. So what I have at work here is that this is my buoyant force. This is my weight. And then I have an additional force here pushing up, which will be some scale. And this scale is reading that he has a mass of 1.5 kilograms. This is just like the video of the lady where she goes into the tank and she goes all the way under the water and then they measure her weight. That's the apparent mass, the mass that you appear to be when you're submerged in this liquid. All right? And I know that this mass, this force rather, is going to equal 1.5 kilograms times 10 meters per second squared. So I want to know what mass of water does he displace? All right, well I can say then that this apparent mass, I'm going to write it as this F scale, that's plus the buoyant force minus the force weight is equal to 0. That's from Newton's second law. I just sum up those vectors. Add the ones that are going up, subtract the one that's going down. Then I'm going to start putting in some numbers here. So I already know that this F scale, if his apparent mass is 1.5 kilograms, this is 15 newtons. That's right here, 1.5 times 10. The buoyant force is going to be the density of water times the volume that's displaced, that's the volume of the object, or the person in this case, times g, minus his actual weight. That's going to be 65 kilograms times 10, which is 650 newtons. So his weight, his actual weight is 650 newtons. All right, now I am looking, this is all equal to 0, I'm looking for the volume of the object, the volume of the person. So I can find that fairly simply. Just solve this for V. That's going to be 650 minus 15. I add 650 to both sides, subtract 15 from both sides, and then I'm going to divide by the density of water and the acceleration due to gravity. So that's 635 newtons divided by the density of water. I'll need it in SI units, 1,000 kilograms per cubic meter. I'll provide that to you, times 10 meters per second squared. And I get 0.0635. This is in cubic meters. So that's his volume, 0.0635 cubic meters. Let me just make sure I got the right number. Answers in the back of the book, by the way, for the odd numbers. Yeah, 0.0635 cubic meters. It looks like that was actually part B, asking for the volume. I also want to know what mass of water does he displace. The mass of water that he displaces is fairly simple. You could find it, actually now that we know the volume is just the density, or excuse me, the mass is just equal to the density times the volume. This is based on our definition of volume, by the way. And so my density is 0.0635. Excuse me, that's my volume, cubic meters. My density is 1,000. And so that gives me 63.5 kilograms. That's part A. This is part B. Another simpler way, actually, is I know that this force has to equal these two forces. So if his actual mass is 65 kilograms and I'm only reading 1.5 kilograms on the scale, then I have to have the difference in that, 63.5 kilograms. That's the mass of water that's being displaced, and the weight of that water is equal to the buoyant force. Okay, I need to calculate his density. So to calculate his density is just his mass over his volume. That's 65 kilograms over his volume, which is 0.0635 cubic meters. And I get 1,024 kilograms per cubic meter. Notice this is slightly more than the density of water, which is 1,000 kilograms per cubic meter. And then I'm also supposed to calculate the fluid's density. Oh, goodness. Oh, no, never mind. If his lung capacity is 2 liters, is he able to float with his lungs filled with air without treading water? Let's just skip that. I think if we stop here, that's probably good. So we'll just skip part D on this question. It's actually a fairly involved question. And on an individual question on the test, you wouldn't have any one part of this, or you wouldn't have it in totality, but you could have any one part of this on the test. Archimedes' principle is fairly important for measuring buoyancy and measuring masses of bodies that you don't know their actual mass, the mass and volume or the density of unknown bodies, like people, for example. All right, that was 23, just a couple more. 28 says normal blood flow in a resting adult is at a rate of about 5 liters per minute. Convert this to cubic centimeters per second. So 5 liters per minute. And I want to convert this to cubic centimeters per second. All right, let's first just do the minutes. 1 minute has 60 seconds. 1 liter has 1,000 milliliters. And 1 milliliter is equal to 1 cubic centimeter, or 1 cc. And so this will give me my final units in cc's per second. So that's 5,000 over 60, which is 83 cc's per second. That's number 28, and then number 43. In a certain venturi, the diameter of the tube decreases from 2 to 0.5 centimeters. 43. I have a tube that goes like this. It's big and then it gets smaller. It initially has a diameter of 2 centimeters. And then it has a diameter of just 1/2 a centimeter. And in the larger part, it has a speed of 50 centimeters per second. And I want to know what is the speed when it comes over here. So I want to know what is this. I'll call this V2. All right, this is the equation of continuity talked about in class. A1 V1 is equal to A2 V2. This just says that if I have a certain amount of fluid over here at a certain rate, all of that fluid has to come through over here. In order for that to happen, since I have a smaller cross-sectional area, it has to go faster, like when you put your thumb over the end of the water hose. All right, so here I have pi times 2 centimeters, that's the diameter, over 2 squared times V1, which is 50 centimeters per second, is equal to pi 0.5 over 2 squared. That's pi r squared. The area is pi r squared. I have the diameter times V2, which is what I want to know. But notice here that it doesn't matter that whether I use the diameter or the radius, because all these things cancel out. So I'm left with 2 squared times 50. That's 4 times 50. And then I divide by 0.5 squared. Divide both sides by 0.5 squared. And that gives me V2. That's equal to 200 over a quarter, which would be 800. 800 centimeters per second. It's the equation of continuity. 43. Yeah, that's the end. Now, there were no Bernoulli's equations on here when we talk about the pressure, but we will see that on the exam, but there won't be any calculation type problems regarding Bernoulli's equation. But you will see that, that is that when the velocity increases in a fluid, that the pressure decreases. So make sure that you're aware of how that works and what it describes, Bernoulli's principle. There's a nice section in the book on it.